we might have some idea that this is the equation of a circle, this of an ellipse, this represents a hyperbola, and this a parabola. But how does an equation like this create such a unique yet fascinating curve? That's what we are going to explore today. There are several curves corresponding to equations such as these, but the world of possibilities is endless. Curves like these that we are familiar with are known as conics and are introduced to us through our elementary knowledge and school curriculum. These are called conics because they are derived from a plane intersecting a double cone. The general equation of a conic is given by a second-degree polynomial in x and y. We can clearly see that the equation we have today is quite different. It is not a conic as it cannot be simplified into a second-degree form. These belong to the domain of polar curves, which become far more simplified when expressed in the polar coordinate system. As some of you might be familiar, the polar coordinate system is a different kind of two-dimensional system. The origin is called the pole, and the reference axis, which is the x-axis, is called the polar axis. Any point can be located using r and theta. R is the distance from the pole, and theta is the angle made by the line connecting the pole and the point with the polar axis. We can convert between polar and Cartesian coordinates using x equals r cos theta, which gives the distance of the point from the y-axis, and similarly, y equals r sine theta. Now, let's use these relationships to convert our equation into polar form. We get r equals sine 2 theta. This is a very simple equation to understand. Here, r depends on theta, given by this function. Let's first draw the graph of theta versus sine theta. Now, let's transform it to sine 2 theta. Consider theta equals pi over 4, gives us the distance, r, of a point at an angle of pi over 4 with respect to the polar axis. Thus, for any value of theta, we can determine r directly from the sine 2 theta plot. At theta equals 0, r is also 0, so we start at the origin. As theta increases, r also increases until theta reaches pi over 4, where sine 2 theta reaches its maximum. From here, the value of r decreases as theta increases until we return to the origin. Now something peculiar happens as theta increases. Instead of going to the second quadrant, we move into the fourth quadrant. Why does this happen? It's because, despite theta being in the second quadrant, the value of r given by sine 2 theta becomes negative, which flips the position to the opposite direction. From here, the curve continues normally and returns to the origin. Then, the curve proceeds into the third quadrant. Once again, as theta moves from 3 pi over 2 to 2 pi, r becomes negative, flipping the point into the opposite direction, which in this case lies in the second quadrant. What began as a complicated equation in x and y has transformed into something peculiar yet remarkably beautiful. Ladies and gentlemen, this is mathematics. Thanks for watching. If you enjoyed this video, don't forget to hit that subscribe button and join us for more exciting and interesting lessons just like this.